Let's talk about polar and rectangular coordinates. So basically we're going to talk about polar coordinates. We usually talk about rectangular coordinates, but we're going to talk about polars. What are polars? Well, they are built like this. R for radius, theta for angle. Rectangular coordinates are x and y, so polar and rectangular. We can take some problems, if we want to, and translate them. How are they related? Well, you probably remember from trig that x squared plus y squared equals r squared is a basic circle. So that relates there. And that x over r is equal to the cosine of theta. Y over r is equal to the sine of theta. And if you want, y over x is equal to the tangent of theta. So a lot of times we use those things to translate between rectangulars and polars. Let's look at some examples. Let's take something that looks pretty common. Here is x squared minus y squared equals 9. Now, if you divide it through by 9, you'd get x squared over 9 minus y squared over 9 equals 1. That's a hyperbola. It's a hyperbola that opens left and right. It is centered at the origin. And you could find the c value. You could go up 3, down 3, left 3, right 3 to get the vertices position. Actually, left and right gives you the literal vertices. And so that would give you your hyperbola. Well, what does a hyperbola look like in polars? Well, you might use some of this. Now, I know that x is equal to r cosine theta if I multiply both sides. So if x equals r cosine theta, then I know that x squared is r squared cosine squared theta. And I know that y is equal to r sine theta for the same reason here. So y squared equals r squared sine squared of theta. So if I put these in place of these, I've got r squared cosine squared theta minus r squared sine squared of theta is equal to 9. The thing about polar coordinates is that we have these, and usually polar functions, and you'll see this when you look on your calculator, but they are f of theta equals r. So we've got to solve for r. So let's factor r squared out, and we get cosine squared of theta minus sine squared of theta, and here we've got equals 9. Now, I love trig, so I notice that there's an identity here. Cosine squared minus sine squared is cosine of 2 theta. Now, that's a lot easier to look at, so that's equal to 9. If I want r by itself, I divide both sides by cosine 2 theta. So r squared equals 9 over the cosine of 2 theta. Well, that is just dividing by cosine theta is secant. So that's 9 secant 2 theta. And so if I want to solve for r, I get r equals plus or minus the square root of this 9 times the secant of 2 theta. Now, that is plus or minus 3. You can take the 9 out and then have the square root of the secant of 2 theta. So there is a translation from rectangular coordinates to polar. Let's go from polar to rectangular. Here's another example. What if I have r equals 5 cosine theta? How do I make that into terms of x and y instead of r and theta? Well, I've got x's and cosines and y's and so forth. So let's solve for x. Now, strangely enough, this one looks a little bit like the last one, but anyway, it's not the same. But if I divide here by 5, then I would have r over 5 is equal to cosine theta. So r over 5 equals cosine theta. Now, the only reason I did that is because I know also that cosine theta is x over r. So that's equal to x over r. So now I know that r over 5 equals x over r. If I want to solve this a little bit better, I could cross multiply. I get r squared equals 5x. Well, what's r squared? R squared is x squared plus y squared. So x squared plus y squared equals 5x. If I move it all to one side, I've got x squared minus 5x plus y squared equals 0. Complete the square, we'd have x squared, 5 minus 5 divided by 2 is 5 halves, minus 5 halves. So I need to add 25 fourths to both sides. So I've got minus 5x and then plus 25 over 4. And then plus y squared equals 0 plus 25 over 4. So I've got x minus 5 halves squared plus y squared equals 25 over 4. So what did this represent? Well, it represented a circle, centered at 5 halves, 0 on y, and the radius is equal to 5 over 2. So we can translate back and forth. Now, polar coordinates also have calculus involved. So you don't just spend time doing these algebraic and trig maneuvers. You may have to find derivatives. So let's find the derivative using calculus. So derivatives are polar coordinates. So derivatives in polar. All right, coordinates. Let me go ahead and put that there. So derivatives. Here's a formula that you will find, and this is based on the same implicit type differentiation that you do with parametrics, because this is just another form of a parametric. So I'd say dy d theta is equal to, or dy dx is dy d theta over dx d theta. Now, a formula that you will see printed a lot of places is this: f of theta cosine theta, and you can justify this if you want. I'm going to just use it, but f prime of theta sine theta, this is divided by minus f of theta sine theta plus f prime of theta cosine theta. Now that looks pretty wild, and it can be validated, so feel free to try to do that. I'm just going to use it, okay? So here's our example. F of theta is equal to r is equal to 2 plus 3 times the sine of theta. All right, so let's take the derivative of that. Well, all right then. Now, dy dx, not the derivative of this particularly, but the derivative dy dx. So dy dx is equal to dy d theta, okay, over dx d theta, but I don't have x and y, so I've got to use this formula. So I've got to take f of theta, so that is 2 plus 3 sine theta, 2 plus 3 sine theta, that's f of theta, multiplied by cosine theta. plus f prime of theta, that is 3 cosine theta, times sine theta. This is divided by minus f of theta, so minus 2 plus 3 sine theta times sine theta. Notice none of these things cancel. And then plus f prime of theta, which is 3 cosine theta, times cosine theta. So now we have to simplify. The simplification, not too bad maybe. Let's take this, 2 times cosine, so it's equal to 2 cosine theta plus 3 sine cosine. So plus 3 sine theta cosine theta, and then plus 3 sine theta cosine theta. The denominator has minus 2 sine theta plus 3 sine squared, or not plus, minus 3 sine squared plus 3 cosine squared. Okay, so there's the derivative. Now you can simplify a little bit. So let me take it over here, and let's take this and put it over here. So this becomes 2 cosine of theta plus 6 sine theta cosine theta, and then that is divided by minus 2 sine theta. Now, for reasons that will become apparent a little bit later, I'm going to turn all these into sines. So minus 3 sine squared, and then plus 3 cosine squared is 1 minus sine squared theta. So we've got this. I'm going to factor here. I've got 2 times the cosine of theta that I'm going to factor out, left with 1 plus, I took 2 out of there, so I've got 3 sine theta. So that's kind of nice. This, I've got all in sines. So I've got sine squared. Let's see, I've got minus 3 of them, minus 3 more. So minus 6 sine squared of theta. Then I've got minus 2 sine of theta. And then I've got plus 3. So if I want to find horizontal and vertical tangents, horizontal and vertical are based on y and x, not on theta and r. So if I want horizontal and vertical tangents, I will have to set these equal to 0. Okay, so set this equal to 0 for horizontal, and set this one equal to 0 for vertical. Okay, so let's do the horizontal. First of all, that's easier of the two. So if we take 2 cosine of theta, that's one factor. So 2 cosine of theta equals 0. Then that means cosine of theta equals 0. Where does that happen? Well, it happens at pi over 2, and it happens at 3 pi over 2. Nice exact values. Where is 1 plus 3 sine of theta equal to 0? Well, that would be where sine theta is equal to minus 1/3. Now, that is not as simple to deal with. So what we'd have to do is we'd have to go like this. We'd have to take arc sine of 1/3. Now, I ignored the minus, and I'll show you why. Because this is going to give us a reference angle. We need a negative sign, so you've got to put in quadrant number 3. Sign is negative there. And then you've got to put it in quadrant number 4. It's negative there. So what you get here has got to be added to pi to put it in quadrant 3. So we're going to have pi plus, and I'm going to use exact values here, arc sine of 1/3. That's the one in quad 3. And then to get it in quad 4, we're going to have to take 2 pi minus arc sine of 1/3. Now you could play calculator with that and do a lot of work, but anyway, those are not very easy problems to work on. You pretty well need a calculator to get some digits, but that's exact. Down here, we've got a quadratic formula problem. It does not factor easily. So if I go through and set this equal to 0 and use the quadratic formula, I end up with this. I end up with sine theta is equal to, now, minus b, so that would be plus 2, plus or minus the square root of b squared, which is 4, minus 4 times a, which is minus 6 times 3, all over 2 times a. So I've got sine theta is equal to these things. Well, I've got 2 plus or minus. See, we've got 4 times 6 is 24 times 3 is 72. That's positive, so that square root is 76. And it's all over negative 12. So we've got two totally different answers here. Well, you might remember from trig that two answers here equal to a sine. Each one's going to have 2. So we're going to have 4 total answers for vertical tangents. All right. You would approach this very similar to the way we did this one. If I take 2 plus the square root of 76, now I know 76 is not simplified, but if I take 2 plus the square root of 76, we have got, let's see, we've got 2 arc sine, so theta is equal to arc sine of 2 plus the square root of 76 over negative 12. That's a negative value. So you might want to make it positive and then push your angle into the right quadrants. That works very well. It worked well here. And then the other one is equal to arc sine of 2 minus the square root of 76 over minus 12. Now that one is positive. So if you turn that one into a plus 12, that'll give you a reference angle. It's a negative value for sine, so then you put in quadrant 3, because sine is negative there, and then you have to put it in quadrant 4. Do it just like this, that works fine. Here, this one is a positive value. So that one's going to automatically give you a reference angle. And sines are positive in quadrant 1, so use the reference angle. And so that one's quadrant 1. And then sine is positive in quadrant 2, so put in quad 2. And that is, you take pi minus your reference angle, and that'll put it in quadrant 2. So you get a lot of really wild answers on that. It hopefully taxes your trig knowledge a little bit, and you can use it on your calculator. So here's what we've done. We've done a lot of things here. We have turned some problems into polar coordinates. We took a polar function and turned it into rectangular coordinates. And then we took the first derivative in polars using this formula, just acting like that was given to us because it was. And then we found horizontal and vertical tangents. And notice what we did. We got 2 horizontals and we got 4 verticals. So if you look at this graph on a calculator, the graph of this thing, 2 plus 3 sine theta, is kind of simple actually, but it looks like almost like a circle. It goes kind of like this, Let me move that over so you can see it. Looks kind of like that. It's called a limacon with an inner loop. Now, I've already put it in here, but if I've got 2 plus 3 sine of theta, and I plot that, and I think this is already plotted, so you're not going to see it plot, but it looks like that. That's called a limacon with an inner loop. Limacon is kind of like a lima bean, and this inner loop is in here. Notice, where does it have horizontal and vertical tangents? Now, I think I told you something a little bit off here because I forgot to count one of them. We had a horizontal tangent for this one, and then we had 2 more, so we actually have 3. One of them is right here, one of them is right here, one's right there, and actually 4, right? There's another one. So there are 4 horizontals and then verticals. There's a vertical right in here, a vertical right in here, there's a vertical here, and a vertical here. So there are actually 4 of each. I miscounted, but I think we found them all. Here are 2 horizontals. Here are 2 more, so there were 4 horizontals. And we had 1, 2, 3, 4 verticals, so we did have all 4. And they are not necessarily at all at nice numbers. Now, one thing I want to just mention at the very end of this is if you talk about this point up here at the top of this loop, that is the point where x, or where the theta value is 3 pi over 2. Now, if you go all the way to 3 pi over 2, it's here. So what it looks like, if you want to figure it out, is it's -1, because you're down here and it pops up and becomes -1. So that's kind of an interesting scenario because it looks like it's at 0, 1, but that's in rectangulars. In polars, it would be called radius of -1, and theta would be 3 pi over 2. And again, that's something else that's different. Radius can be negative. So think about that a bit, and there you go.